Yes, we are still very much at the network layer, but the good news is we are done with the majority of the functionality. We covered this, we covered this, we covered this. The only piece remaining is this. So in the next few videos, we will wrap up routing. In this video, I'm going to provide an overview of routing. The details will come later. But first, a few recap questions. So the role of the network layer is to forward a packet from a source host to a destination host. And as part of this forwarding, it looks at these forwarding tables. So how are these forwarding tables built? That is part of the routing protocols. So that's what we are focusing on currently. I mentioned this before, but let me emphasize again, there is a difference between routing and forwarding. The task of forwarding is to get a packet, look at the destination and decide on which output port at the given router this packet has to go. So for this, it consults a forwarding table. The task of routing is to build such forwarding tables. A terminology that we are going to use in the future is routing domain. Basically, all routers that fall under the same administrative control fall in the same routing domain. For example, routers within a university network like IITB fall within one administrative domain. Similarly, routers that belong to an ISP network fall under a different routing domain. So it's possible that you could employ different routing protocols in each of these routing domains. Routing depends heavily on graph theory. Here is a graph. So this graph has what are called nodes and edges between the nodes. These nodes are also called vertices. And an edge is often associated with a cost that is represented here. And if there is no edge between two nodes, like there is no edge between A and E, one can view it as an edge with infinite cost. So how does a graph relate to the networking domain? Basically, these nodes that are part of the graph could be either hosts, routers, or networks. So for now, we will view these nodes as routers, but later I will get into how things are done in practice. And these edges between the nodes actually correspond to the physical links. And these costs translate to the cost of moving a packet on this particular link. By the way, cost doesn't necessarily mean money here. It could capture the time it took for a packet to go from A to B. Another term that we will use is neighbors. So a node has certain neighbors, which are the nodes that are directly connected to this. So for example, the neighbors of node A are node B and C because it has direct links with them. So what is the goal of routing? Basically, it looks into finding the least cost path between two nodes. And the cost of a path is nothing but the sum of the costs of the individual edges. For example, if I'm trying to find a path between nodes A and E, if I look at this figure, here is one path. And this path has a cost 1 plus 9, that is equal to 10. Here is another path. And this path has 1 plus 3 plus 4 plus 2. This is also equal to 10. And there is another path like this. And the cost of this path is 11. So either of these two paths can be the least cost path. By the way, an assumption we make henceforth is this graph is undirected graph, where if I look at two nodes A and B with a link, and it having a cost of 1 means it's the same cost if a packet went from A to B or a packet went from B to A. But there could be directed links, in which case the cost of going from A to B could be 1, but the cost of going from B to A could be 10. So in my explanations later, I will focus mostly on undirected graphs. So where were we? We were looking at finding the least cost path between two nodes. Often this problem is called the single pair shortest path problem. Often in routing, we are more interested in this particular problem, that is a single source shortest path problem. What this is you try to find the least cost path from a source to all the other nodes in the graph. Why do you think this is the focus in routing? Often when a packet comes to a router, this could be destined to any of the hosts that are being served by the individual routers. So you need to find the shortest path between this router to any of these other routers. And you want to do this in an efficient fashion. That is where the single source shortest path problem comes into play. So this is a very well studied problem in graph theory. If you have already done this subject, you would have come across Dijkstra's algorithm. But if you haven't done it, I would suggest that you read up on Dijkstra's algorithm. I will not get into the details of these algorithms as part of this course, but I will mention one principle that is employed by many of these routing protocols, that of the optimality principle. Suppose this is the least cost path between two nodes X and Z, and let's say Y is an intermediate node on that particular path. By the way, there are other nodes as well. I'm just focusing on one intermediate node Y. Given that this is the least cost path between X and Z, what can you tell about the path between Y and Z? It turns out that this is the least cost path between Y and Z. Why? If indeed this was not the least cost path, you could replace this path with this other least cost path, thereby being able to go from X to Z over a even lower cost path. So this violates this assumption that we made that this was the least cost path between X and Z. So basically, if an intermediate node Y is on the optimal path from X to Z, Y to Z is also an optimal path. Now, given this rule, answer this question for me. Suppose you have this network topology graph and I have identified one node, let me call this the destination node, and I'm going to mark on this graph the optimal paths from all these other nodes to this destination node. What will these marked up paths form? Well, basically they will form a sync tree rooted at the particular destination. Because you're trying to find out the shortest path, they will all form a tree to this particular destination, because as I mentioned, if this is on the shortest path, this also will be on the shortest path. So here are some features of this sync tree. One, it need not be unique. You can have multiple sync trees. Because it is a tree, there are no loops possible, which means that each packet can be delivered within finite hops. And another useful feature is for undirected links, a given source to all destinations also forms a tree. So this tree, you're trying to find out the shortest path from different source to this particular destination. But if you flip it where this becomes the source and you're trying to find out what is the shortest path to all these other nodes, because the graph is undirected, the same tree will work. So the goal of the routing algorithms is to help find such sync trees for all the routers. So I hope this makes it clear as to what we are trying to achieve as part of the routing algorithms.